Okay, let's continue looking at satellites in this one. If you've got satellites going around the Earth, they need to have an orbit where the centre of orbit is actually the same as the centre of the Earth. Okay, and that doesn't matter if it's actually a polar satellite or a satellite going around the equator here, or even a geostationary satellite, which we're going to talk about later on. There's no good having an attempt to get an orbit that's like this, because it won't work. Because the centre of the orbit is not the same as the centre of the Earth. So why does the actual centre of the satellite's orbit have to be the same as the centre of the Earth? If you ask that question, so why do they need to coincide? Well, there's 3 points you normally make. One point to make will be that any object travelling in a circle needs a centrifugal acceleration acting towards the centre of its orbit, or circle. So that's the first one. Now, a force is needed for this. So the force that's providing this acceleration, providing the centrifugal acceleration, is gravity. Right, it's a gravitational force between two bodies. And lastly, you need to point out that that force actually acts between the centre of the masses. So what we're saying here is it's really important to point out that for the orbit point of view, we need a full acceleration towards the centre of the orbit. Okay. Secondly, that force that's providing that is actually due to gravity, that one there, which is the force between any two objects. Okay, that one there. Now obviously, if this force acting between the centre of mass of the Earth and the centre of the satellite, we need to have the orbit centre coinciding with the centre of the Earth. Okay, so you've got to point out centrifugal acceleration is acting towards the centre of the orbit. Okay, there's a force providing this, and it's gravity, and the force acting between the centre of masses of the satellite and the Earth. Now let's look at some different types of satellites here. So two key ones, geostationary and polar, we'll look at later on. Alright, so let's check a geostationary. So geo means the Earth, stationary means it's stationary relative to the Earth, or it's still. Okay, so if you're looking at this here, if that was the Earth, you actually find, well, we're going to put the Earth actually flat here. If that's the equator, you'll find a geostationary satellite a fair way out, and it's going to be orbiting with the Earth, so that if you're looking for a point above the Earth's surface, the satellite would always stay in that same point relative to the Earth. So as the Earth turns, this is going to turn in exactly the same period. So it stays above the same point above the Earth. So that's what geostationary means. Relative to the Earth, it's going to stay stationary. Okay? Please don't put in your answer that it is a still satellite, okay, that it's not moving, but because it is moving, it's just at the same period as the Earth and staying with it. So what sort of properties does it have then based on that? So properties of this that you need to be aware of. One, we can say it's got a period of about 24 hours, same as the Earth's rotation rate, or rotation period. It also needs to stay above the equator. Now, there's a reason for that. If it was not all above the equator, it was actually down here, like that, and trying to stay with the point, say, above the Australia there, would it have a centre of orbit the same as the centre of the Earth? No. So the force needed to keep it in that orbit would actually be towards the centre of the orbit, but the force supplying it is towards the centre of the Earth. And if the two aren't matching, and there's a satellite there and it's actually pointing that way, then you're not going to get a stable orbit. So you can't get a geostationary satellite anywhere other than above the equator. Okay. The other things to keep in mind here is it's got a very large radius. Now, why can you argue that? Well, if you remember earlier on, we talked about the fact that r cubed was proportional to t squared. And what we've got here is a very long period. So if you've got a long period, you must have a large radius. So it's got to be placed a long way away. Okay, and we've used that formula before, and you could calculate it just exactly how far away it needs to be to have a period of about 24 hours. Okay, it's a large radius. What else can you tell me here? Now, obviously the Earth is rotating from west to east, so the satellite also needs to rotate from west to east. Okay, so it's rotating west to east, large radius, 24 hours, and it's above the equator. You can look at some advantages of this one here then. It'll see one side of the Earth very well all the time. Okay, so it's virtually looking at a half of the Earth, I mean it's a long way away, all the time. So it's got a good view of the Earth the whole time. So a large section of the Earth can be observed continuously. So that's a good use of it there. Other things are you do not have to track it. Do not have to track it across the sky. So you do not have to track it across the sky because it's always in the same point. So that's good for communications. Okay, you can always have your satellite dishes pointed at that one satellite, and it'll give you the feedback or send the message somewhere else. So there's two big advantages of it. So usage you can get out of that then would be communications, satellite TV, GPS and so on. Right, let's look at the other type. Now the polar satellites actually orbit around the poles and here. Okay, so you've got North Pole, South Pole, and what's happening beneath it is the Earth is turning underneath it. So when you look at this, what will happen is the satellite will do an orbit and it will actually be able to see a strip of the Earth there. And it'll be able to see that strip of the Earth in high detail and from a good angle of 90 degrees directly above the Earth. So the feature of this satellite then is it's got a small radius because it's very close to the Earth. And the reason for that is because it's got a short period. They want the satellite to be going around in a very short period of time so it gets lots of views of the Earth as the Earth turns underneath it. So don't forget that idea of r cubed and t squared being proportional. So it's very close. Typically you might be looking at about 90 to 100 minutes for one of the orbits, and therefore it's going to be a very short distance away from the Earth. So what's happening here is as the satellite makes a new pass, the Earth has moved on and you get a new strip of the Earth looked at, okay? So they'll look at this strip next, and then the strip around the back, and so on until you've got the whole of the Earth covered. And you should be able to get 2 whole views of the Earth each day, all right? So the fact it's got a short period allows it to rotate relatively quickly around here, and the Earth is turning slowly beneath it. You'll get the whole Earth in twice a day. So if we look at the individual properties here, we've actually said it's got a short period. Because of that, in this idea here, it's got a small radius. And the thing to be aware of is it's rotating around north to south around the poles there, and the Earth is spinning beneath it while it's doing that. So what advantages would that have, or what uses would that have? Well, first of all, if it's actually close to the Earth's surface, it's going to give you higher resolution pictures because it's a closer distance. So, 2 key things here. The low altitude orbit allows it to give you high resolution pictures, and it's from 90 degrees as well, which is really good. As opposed to geostationary one of the disadvantages are you can't see the poles very well because you're looking at it out here from a long way away, and it's very hard to see what's going on at the poles because it's a very oblique angle there. So that's something to keep in mind. This does not do that. It's got a good view from 90 degrees directly above. It also views every part of the Earth each day. In fact, it's twice in every 24 hours. Now, what uses will that have? So, really good for looking at weather and surveillance. Okay, as uses because of those reasons there.
Polar satellites are the satellites which pass over the north and south poles of the Earth. Since the Earth is rotating about its axis, these satellites pass over different parts of the Earth during its revolution. They generally revolve very close to the surface of the Earth. These satellites are employed by the Army for spying and surveillance of the movements of tanks and ships and other vehicles. They are also used for weather monitoring and remote sensing.
So this shows you a geostationary satellite. It does give you one misconception though, because the video shows the geostationary satellites being relatively low, when it's almost about 5.5 Earth radii above the Earth. So if you're going like that, you should be doing 5.5, so it should be a fair way out. But apart from that, it's quite good.
Geostationary satellites are those satellites whose period of revolution around the Earth is equal to the period of rotation of the Earth. Geostationary satellites appear to be stationary as they revolve around the Earth from west to east. The period of revolution of the satellite is equal to the period of rotation of the Earth, and they revolve in the equatorial plane. The orbits followed by geostationary satellites are called geostationary orbits or parking orbits. The height of the geostationary orbit is approximately 36,000 kilometers above the Earth's surface. The orbital velocity of a geostationary satellite is nearly equal to 3.08 kilometers per second. Geostationary satellites are used for communication purposes.
So let's recap this. The centre of orbit of the satellite orbiting the Earth must coincide with the centre of the Earth. Why is that? So 3 key points to make. Centripetal acceleration is needed towards the centre of the orbit to keep it in an orbit. Okay, it's the same as any circle. The gravity is the force providing this, supplying this acceleration, and that acts between the centre of the 2 masses, so the centre of the satellite and the centre of the Earth. So making those 3 points in any order will normally give you good marks in that. Okay, so they've got to coincide. Geostationary satellites means it's going to stay over a fixed point above the Earth's surface or relative to the Earth's surface. And the features of that, or the conditions of that, is it's got to be equatorial, the orbit, so it's got to be above the equator. The period's going to be about 24 hours to match the Earth. Oh, it should be circular, I mentioned that. And it requires a stronger signal. Oh, that's actually a disadvantage and not a feature of the orbit, but it's actually something, one of the properties you can discuss later in terms of effect, in terms of usefulness. And larger orbital radius, because the idea is it's got a larger period, it must be put up there at a higher radius to get a stable orbit. We've shown that before in the last part. And it should be rotating from west to east to match the Earth's motion. The advantage is there, it stays in the same spot, so you don't need to track it, and you can see a large portion of the Earth all the time. So some disadvantages that we haven't actually really gone through. It can only be above the equator. It has to be a large distance away, so you're going to get a time delay in the signal, and you can't be used for imaging around the poles, and it's also low resolution, so it's got some weaknesses there. But it has some uses: communication, GPS and satellite TV, because it's in that fixed spot. Now with the polar one, don't forget that it orbits around between the north and the south poles while the Earth's going beneath it. Okay, you can see that here in this picture. With the radius and period chosen so that it actually rotates under it. Now a really well thought out one will actually pass over the same location each point each day, by the way, so you can actually set it up to do that. So don't forget, as it's going through there, then it's going to give you a different strip of the Earth. That advantages there would be high resolution because it's closer to the Earth, and because of the shorter period there and the fact that it sees a different strip at each rotation, you're going to see all of the Earth every day, twice a day. Okay. You also get good images of the poles and a negligible time delay here because it's closer. So there's other uses of that then would be looking for weather and surveillance and stuff like that. So what are the advantages of launching satellites from near the equator? So if you consider any satellite that's going to be following around west to east, a geostationary one or even a low Earth orbiting one that happens to be going around in this direction, why would you want to launch it from this area here rather than down here? Well, if you think about it, you've got V equals 2 pi r on T. Okay? And anything on the Earth's surface here will have a period of about 24 hours, same as the Earth. What will vary though is the circle plotted out by the different positions on the Earth. If you're up near the poles, you'll only go around this circular part in a rotation, which is not a very big circle, and therefore it's got a small radius. If you're near the equator here though, you're going to go around this sort of size circle on every 24-hour period. So you'll travel further here, therefore your linear velocity on the Earth's surface is actually higher near the equator than it is at the poles. What advantage does that have? Well, if you've got, we can actually calculate it, I think it's about 465 metres a second at the equator. If you've already got this speed here near the equator, to actually go and achieve an orbiting speed of maybe, say, 7,000, the increase in speed you need is smaller than if you start at, say, 150 metres a second. And if the increase in velocity needed is less, you can use less fuel to get up there, and therefore it's cheaper. So you can look at that in this PowerPoint here as some key points. If you look at this one here, the Earth is already rotating from west to east. The equator has the max linear speed, so therefore the satellite is already travelling at that speed, and it will need a smaller increase in speed. So it's going to have a smaller increase in speed because of that high speed there, therefore less fuel and therefore cheaper. So that should be the end of it. Thanks. And thanks to Mr. McGarry for those excellent PowerPoints.